Yeah, I forgot to start the recording. Okay. So we have started with the discussion of comparators, where a comparator is a circuit which is going to compare your input bits A less than B, LT is equal to 1, and A equal to B equal to signal is will be equal to 1, and A greater than B, GT will be equal to 1. So this is a truth table of this particular comparator, where if A is less than B, your less than signal will be equal to 1, and if A is equal to B, this equal to signal will be equal to 1, and if A is greater than B, this particular Z signal will be equal to 1. So is this clear? The explanation of the comparator is clear. Shall we move to the conclusion part, which we were discussing earlier? Yes? Yes or no in the chat box, please? So the comparator is clear? Yes, yes. Now, so the conclusion which I was drawing is, yeah. So let's say if we have any design, okay, any combinational logic circuit, okay, it may be comparator or it may be some adder, subtractor, multiplexer, demultiplexer, encoder, decoder, okay, anything. First, you should know the truth table, okay. Truth table gives you the functionality of your particular design, okay. If any particular input is given, how the outputs are being generated, okay. So the truth table will describe the behavior of your particular combinational circuit. Okay. First, draw the truth table of that particular design. Now, after drawing the truth table, from that particular truth table, derive the Boolean expression. Okay. From the truth table, derive the Boolean expression. Derive the Boolean expression. What type of Boolean expression, whether it is minimized or non-minimized, which Boolean expression you should use, minimized one or non-minimized one?
Minimized one.
Yes. So derive the minimized Boolean expression from the truth table. Okay. Then from that, develop the logic for that particular combinational logic. Is it clear how to design a particular combinational logic, combinational design, how to create a combinational design? Is it clear? Yes or no in the chat box, please. Now, can you able to design any combinational design if a particular requirement is given to you? Yes. Yes or no in the chat box, please. Yes. Very good. Very good. Someone has unmuted their mic. Please mute. If you have any doubt, you can unmute. I think Shailesh. Yeah. Thank you. So if you have any doubt, you can unmute. Okay. No problem. Yes. Okay. Very good. So are we good? Is it clear, everyone, how to design your combinational logic? Is it clear? It may be any combinational design, irrespective of any combinational design. If you know the functionality of a particular combinational design, if you are able to derive the truth table, then rest is simple. You just apply the key map techniques which you have learned previously. Just apply. Not only this digital design in your when you are working in some industry also. Okay, so when you're working in industry also, if you have any requirement of designing a particular combinational design, okay, just follow the steps which we have followed now, okay, for designing a particular combinational circuit. Okay. Next, so this was about your one bit magnitude comparator, and these are the equations which you have, and how to draw the logic diagram. So from this we can simply draw A naught and B naught. Okay, A naught is nothing but A naught B naught is given to bubble, and A naught bar B naught. Okay, and simply you can use here A naught B naught and X naught gate, and A naught B naught bar. So this is your logic diagram for your one bit magnitude comparator. Is it clear for everyone? Can we move forward? Yes, yes. Next. Next is 2-bit magnitude comparator. So your input bits will be equal to 2 bits. That is, A will be of 2 bits and B will be of 2 bits. Okay, so the truth table, if you know, then you can draw that particular logic diagram. So here it is 0 0 and 0 0. So these two are equal, so our y which is equal to 1, and if it is 0 0 and 0 1, it is less. Okay, so a less than b, x will be equal to 1. Okay, And similarly, you can derive all these particular states. Okay. Now, so these are the possible states. So how many possible values we have? Since there are four variables, we have 2 power 4, which is meant by 16 values we have. Okay, so 4 zeros to 4 ones, and for all this you can have this. Okay, so your simple assignment is, please draw the logic diagram of 2-bit magnitude comparator. 2-bit magnitude comparator. Just try to write the Boolean expression, write down the Boolean expression, and also draw the logic diagram of this particular Boolean logic diagram of this particular 2-bit magnitude comparator. Can you all do this? Yes or no in the chat box? Yes? Very good. Yes. Very good. Yes. Okay. Yes. Very good. Very good. Now, so let us start with another combinational design, which is nothing but your multiplexer. Okay. So let us see what is meant by this multiplexer. Everything. So a multiplexer, abbreviated as MUX, is a digital switch which selects one of its many inputs to a single output. A number of control lines determine which input data is to be routed to the output. If there are n select lines, then the number of maximum possible input lines are 2 power n. And the multiplexer is referred to as 2 power n to 1 multiplexer, or 2 power n cross 1 multiplexer. So for a multiplexer, there will be total inputs which will be equal to 2 power n, and outputs will be equal to only one output. Okay, so the inputs will be equal to 2 power n, and our output will be equal to 1. And which input should be mapped to the output will be decided by a control signal which is known as select line. Select line. And for a 2 power n input multiplexer, how many select lines are there is decided by this particular power n. Okay, so for 2 power n inputs, we will have n select lines. Okay, so this is your inputs, and this is your select line. N is your select line. Now, for a 4 cross 1 mux, what is this 4 indicates? What is this 4 indicates? For a 4 cross 1 mux, what is this 4 indicates? Quickly in the chat box, please. Yes, very good. And how many select lines are there for this 4 cross 1 mux? How you are going to decide? How you are going to decide what? How many select lines are there? 2 select lines. How you are going to decide it? 2 power 2, which is equal to 4. This 2 is nothing but your number of select lines. This 2 is nothing but your select lines. Very good. Yes, very good, very good. Now, so this is a 2 power n cross 1. Okay. So only we have one input, one output. Okay. And we have 2 power n inputs. 2 power n inputs and only one output. Only one output. And how many number of select lines? We have n number of select lines. We have n number of select lines. Okay. Now, so let us say if we consider a 2 to 1 mux, okay. So for this 2 to 1 mux, we have two inputs, let's say I naught and I1 are our inputs, and this is your select line S, and this is your output Y. Now, if select is equal to 0, then my Y will be equal to I naught, and if select is equal to 1, then my Y will be equal to I1. That's it. So depending upon the select line, your output is being decided. Okay, depending upon the select line, which input should be mapped to the output is being decided. So if S is equal to 0, Y will be equal to I naught, and if S is equal to 1, Y will be equal to I. So if you want to draw the truth table for this is a truth table for your multiplexer. That is S select line depending upon if it S is equal to 0, Y is equal to I naught, and if S is equal to 1, Y will be equal to I1. And this is your Boolean expression for your multiplexer. Y is equal to S naught bar into I naught and S naught into I1, which is equal to Y. And this expression has one more name. Can anyone tell me this expression name? Anyone has any idea of this expression name? Y is equal to S naught bar I naught plus S naught into I1. Anyone have any idea about what is the name of this expression?
Shannon's equation.
Yes, very good. So this expression is also known as Shannon's equation. Yes. Okay. So you can also use this particular expression for solving the output y. So the 2 cross 1 mux, is it clear? Can we move forward? Yes. So depending upon your select line, if it is equal to 0, you can substitute here. So if s is equal to 0, then output y will be equal to simply I naught plus 0, which means y is equal to I naught. And if s is equal to 1, then your y will be equal to s naught bar. That means it will be equal to 0 plus I1. So y will be equal to I1. So from this expression also you can derive the output y. Okay? Yes. And in some problems, you will have notations like this 0 and 1 written inside this. Has anyone seen this particular notations which is written inside your multiplexer 0 and 1? Anyone saw this particular notation? 0 and 1 written inside your multiplexer? Yes, very good. So that means 1 minute. Yes. So let's say if you have this particular expression, this 0 is for first pin and 1 is for second pin. So in some designs, you will be written like this S10. Okay, this is nothing but I naught and this is nothing but I1. Now, so if S is equal to 0, what is your output Y? If S is equal to 0, what is your output Y? If S is equal to 0, then what is your output Y? If S is equal to 0, then what is your output Y? Anyone? This is your multiplexer design. Okay. And if S is equal to 0, what is your output Y? I got only a few answers. If S is equal to 0, what is your output Y? I'm talking about this design, this one in the red lines. So if S is equal to 0, my Y will be equal to I1. See the notation here 0 is being written and here 1 is being written. Okay. So if S is equal to 0, my Y is equal to I1. Is it clear for everyone? So please see the notation. If anything is not given, then you can follow the normal thing only. But if it is explicitly written here 1 0, so 0 means it is the first pin. Okay. So if S is equal to 0, this pin will be selected. And if S is equal to 1, this pin will be selected. Is it clear for everyone? Yes or no in the chat box, please. This type of questions you have, I think you have seen in the gate also. So this is a particular confusing type of question. Okay, so we generally do mistakes in this particular things. Okay, so please be careful when you are attending any interviews also, any written test also. Please be careful in this particular points. See the notations. If nothing is written, you can. Okay, once again I will tell. So this is 0 represents, it means it is a first pin and 1 is the second pin. So if s is equal to 0, what we should select? The first pin we should select, that is I1. And if s is equal to 1, we should select the second pin, that is this one. Okay. If nothing is written, then we can follow this default one, that is s is equal to 0, this pin we can select, and if s is equal to 1, this pin, second pin. Okay. Is it clear? Is it clear for everyone? Yes or no in the chat box? Fast. Only few answers. Only few people understood or what? Yes. 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 Very good. Very good. Now, so this was about your 2 cross 1 marks, and this is a diagram. You can draw it. Okay. I think you can draw this diagram, right? No need for me to explaining how to draw the diagram. Now you are able to draw the logical diagram. Yes or no in the chat box, please. So 4 to 1 marks also same. Okay, depending upon the select line. If S not S1 S not is equal to 0 0, your output will be equal to I naught. 0 1, your output will be equal to I1. 1 0, your output will be equal to I2, and 1 1, your output will be equal to I3. Okay, y is equal to this is your Boolean expression. Y is equal to S naught bar S1 into S1 bar into I naught, S1 bar S naught into I1, S1 S naught bar into I2, and S1 S naught into I3. And this is your logical diagram. Okay, this is your block diagram. I naught, I1, I2, I3. Okay, so this is your logical diagram for your 4 cross 1 marks. So is it clear for everyone? The 4 cross 1 marks, 2 cross 1 marks, 8 cross 1 marks, 16 cross 1 marks, 32 cross 1 marks, everything is it clear? Yes or no in the chat box, please? So do I need to explain the 16 cross 1 marks, 32 cross 1 marks, 64 cross 1 marks, everything? No, right? Only 2 cross 1 marks and 4 cross 1 marks. Is it enough, right? Yes. Yes. Now, now. So let us see. Let's say if we want to design a 4 cross 1 marks using 2 cross 1 marks. If we want to design a 4 cross 1 marks using a 2 cross 1 marks, then can anyone tell me how many marks we need for designing this? Okay, okay. Let's see how to design a 4 cross 1 marks using a 2 cross 1 marks. Okay, so for that, first you need to draw the truth table. Okay, so how many select lines are there for 4 cross 1 marks? 2. Let's say those are S1 and S0, and this is your output Y. Okay, so if it is 0 0, your output is I naught, and 0 1, your output is I1, and 1 0, your output is I2, and 1 1, your output is I3. So this is a truth table for 4 cross 1 marks. Yes or no? Yes. Now, so here, can you observe any pattern in this particular truth table? Can anyone observe any pattern in this particular truth table? Can anyone observe any pattern? Any pattern? What is a pattern? Can anyone observe any pattern? In this particular truth table, can anyone observe any pattern? No one?
S1 will be 0 0 and 1 1, and H2 will be triggering like 0 1 0.
Yes, very good. So this is so here for S1, if it is 0 and S0 will be equal to 0 1. And if so, here S1 is 0 and S0 is 0, your I0 is being selected. And S1 is 0 and S0 is being triggered, your I1 is being 1. So for this, how many here one multiplexer can be designed using this, and here one more multiplexer, and this is another multiplexer. So that means you can connect S0 to two multiplexers. So like this, okay. So this is your S0, and this is your I0, and this is I1, and this is I2, and this is I3. Now these outputs are connected to another multiplexer. Okay, and what is the control line? We have S1. Now, if S1 is equal to 0, this pattern, first pattern, if S1 is equal to 0, then this particular multiplexer will be selected. And if S0 is equal to 0, then your I0 will be selected. And if S0 is equal to 1 and S1 is equal to 0, this I1 will be selected. And S1 is equal to 1, then this second pattern will be selected. So S1 is equal to 1, this one will be selected, that is I2. And if S1 is equal to 1 and S0 is equal to 1, your I3 will be selected. So this is how you are going to identify and you are going to build your multiplexers. Is it clear for everyone? Yes or no in the chat box? Yes, is it clear? Now, let us say if we want to build 5 cross 1 mux using 2 cross 1 mux. Okay, then how many number of select lines we should have for 5 cross 1 mux? How many number of select lines we have? Any idea?
For n number of select lines, 2 power n number of inputs will be there.
Yes.
So
So,
it, n is 5, then 2 power 5 inputs.
uh, no, actually. So, let's say if we have a 4 cross 1 mux, then how many number of select lines we have? Two select lines. Now, if we have one more select line, one more input, then is two select lines enough? If we have five inputs, then two select lines are enough? No. So
No,
we
I
should,
guess not.
yes. So we should have one more select line. That is three. So total we have three number of select lines. So if we have three number of select lines, then how many inputs will we have?
2
Eight.
cube.
8. Okay, so we have 8 inputs, but what is our design? We have to design our 5 cross 1 mux. So we are going to ground three inputs. Okay, and we are going to utilize only 5 inputs. Okay, first let us write the truth table: s2, s1, s0, 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1. I naught, I1, I2, I3, 1 2 3 4 5. So here we should stop. Is the truth table clear for everyone? How to draw this truth table for the 5 cross 1 mux? Is it clear? Yes or no in the chat box, please? Yes. Others, is it clear? Only I got a few responses. Yes. Now, so now how to observe the pattern? So this is one group, 0 and 1. This is another group, 0 and 1. Okay. And this is 0, 0 is one group, and this is another group. And we have left with this particular last one. Okay. Now, so here we have one multiplexer, 2, and this is 1, 2. So total 1, 2, 3, 4, 5 multiplexes do we have? Okay, let us see how we are getting this. So this is one multiplexer, and this is one more multiplexer. Okay, so this is 1, 2. Now, so here we will connect I naught, and here we will connect I1, I2, I3. Okay, this is S naught. Okay, and the output is connected to one more multiplexer, which is nothing but your S. No, not like this. Can anyone try this? Can anyone try and let me know in the why we took three select lines? Just now I explained, right? So for a 5 cross 1 mux, how many inputs we have? 5 inputs. So is there any multiplexer with 5 inputs? Is there any? No. So we have 8 cross 1 mux. Okay, but we should have 5 inputs. Okay, so we are making the remaining as ground. Okay, so for 8 cross 1 mux, how many select lines we will have? So for 8 cross 1 mux, 3 select lines. Okay, so we are utilizing 3 select lines. Okay, but remaining combinations we are not taking. 6 muxes are required. Okay. Please try this one and let me know in the assignment. Okay. So please try this one. Okay. So please try this one and let me know. Can you all try this one with the logic which I have explained? Can everyone will try this one? Yes or no? Yes. And also we can also use this multiplexer. We can use this particular multiplexer for building AND gate, OR gate, NOT gate, and XOR gate, XNOR gate. We can build any gates using this particular multiplexer. Okay, so you can also try how to build yeah, once try this question, okay? So it is an interesting question, okay? Once try this on your own, you will make more mistakes and you will conclude so many things, okay? So once try this 5 cross 1 marks using 2 cross 1 marks. Once try this one, I will explain, okay? No issue. Once try this on your own, yeah, it will be interesting question. Designing odd number of inputs is a bit interesting question. Even number of inputs, we can easily build 6 cross 1 marks using 2 cross 1 marks. Okay. But building odd number of inputs is some difficult task. Okay. Once try this one. Will you all try this or should I explain? Yes or no in the chat box, please? Yes. I like the sportiveness. Very good. Yes. Very good. Okay. So you can also build all the logic gates with using this particular 2 cross 1 mux. Since the time is limited, we will try to discuss with this particular answer and the building of logic gates in next session. Okay. Yeah. So that's all for this session. So if you have any doubts or queries, you can stay and ask me. And please wait, I will share the attendance link. Please try this question. This will be very good learning. Once try this. Today's day 11, right? Day 11 or day 12? Day 12. I didn't get your question, Shailesh. Please. No issue, Dipti. No issue. Take care. First, your health is very important. Take care. Take care. No issue. So after filling the form, you can leave the meet. Okay. Thank you. Okay then. Good night.